China just announced a new way to build microchips that will bring them to 1.4 nanometer transistors without leading-edge lithography. Instead of shrinking transistors, Huawei wants to shrink something else: time. I've been designing advanced chips for over a decade, and when I heard this announcement and new scaling law, I had to dig into the details. So in this video, let's find out if this breakthrough is as big as it sounds, or even bigger. For decades, the semiconductor industry had a simple recipe: make device smaller, pack more of them into the same area, get more performance at lower cost. That's essentially what made Moore's law so powerful. But today, that formula is started to break. The progress isn't doubling anymore. Each new generation delivers smaller gains while becoming dramatically more expensive. In fact, with the upcoming A14 transistor generation, TSMC is fighting for roughly a 6% area gains. But Huawei has even bigger problem. Unlike TSMC or Intel, Huawei cannot buy EUV lithography systems, the giant machines that print the most advanced transistors on Earth. The amazing engineering behind that machine made modern 3nm and 2nm chips possible. Huawei and SMIC have pushed older DUV lithography far beyond anyone thought is possible. While they're building domestic alternatives to EUV, their practical solution today is increasingly aggressive multi-patterning. Instead of printing one extremely small pattern in a single step, they split it into several simpler ones. Print the first part, etch it, print the second part, etch it again, and essentially use older machines to create structures smaller than those machines were ever designed to produce. Using this approach, SMIC has managed to push into what many consider a 7nm equivalent process. It's clever engineering, but it comes at a cost of more processing steps and more opportunities for things to go wrong. But eventually, they hit the limit of how far you can keep pushing the process. And so they were forced to start thinking outside the EUV box. What if the future of scaling is no longer primarily about making transistors smaller? What if we are optimizing the wrong thing? Huawei's answer is surprising. Let's fold the chip, literally. To understand why this might actually work, we need to talk about the real problem. Because here is something most people don't realize. Modern computers are no longer limited only by computation. Increasingly, they are limited by distance. And once you see the numbers, you can't unsee them. According to Huawei, more than 80% of the energy can be spent moving data rather than performing computation. Think about that for a moment. This colossal data center isn't spending most of its energy thinking. It's spending most of its energy moving information from one place to another. And that completely changes how you think about performance. Everything comes down to what is called RC delay. And you can think of a modern chip as a giant city of transistors connected by a massive network of tiny metal highways spread across more than 20 layers. Every signal has to travel through those wires, and every wire comes with a baggage. First of all, resistance. It slows signal down. And then capacitance acts like a tiny parasitic battery that must be charged and discharged every single time information moves. And the longer the journey, the worse both become. That's actually the main reason why CPU and GPU clock frequencies barely increased for years. For decades, chips have been mostly flat. Take a look at this NVIDIA GPU. It's 340 billion transistors spread across two flat pieces of silicon. Here, logic cores sit next to each other. Information moves sideways, sometimes across several centimeters of chip area. And every one of those trips takes time and costs energy. The industry spent over 60 years shrinking devices, shrinking transistors. But today, one of the biggest obstacles isn't the transistors, it's the distance between them. And once you realize that, a completely different solution emerges. Instead of building outward, you start building upward.
At this very moment, the logical folding miracle occurs.
imagine taking a large sheet of paper and folding it. Points that were far apart suddenly become neighbors. Huawei wants to do the same thing with chip logic. Parts of the processor that would normally sit side by side are separated and folded on top of each other. What once required information to travel millimeters across a chip now might require only a few microns of vertical travel. And this idea sits at the core of Huawei's tau scaling strategy. And actually, Einstein showed us that time and space are fundamentally correlated. For a long time, our industry has been obsessed with making transistors smaller. Huawei is betting that the next leap in computing will come from mastering time. Tau scaling focuses on reducing the time it takes information to move through the system by shortening timing path and reducing these RC delays. And suddenly, the boundaries between chips start to disappear, and you can start building in the third dimension, like a multi-floor house. Well, with one additional floor, for now. And on paper, that is a fantastic idea, until you run into a huge elephant in the room, the reason why nobody has been building chips this way all along. And the one breakthrough Huawei announced that might finally make it possible. We will get to that in a moment. But in fact, the biggest challenge in technology is not finding the best ideas, is keeping track of them once you heard them, and actually knowing what to do with them afterwards. That's why one thing I carry with me to every conference and every meeting is not a notebook. It is this: the Plot Not Pro. The thing is, my best work sometimes is not happening at a desk. I'm constantly at technical conferences, founder meetings, and engineering discussions. And every time I hear a great idea or an action item, I want to capture it. And this makes it incredibly easy. It's about the size of a credit card, attaches magnetically to the back of my phone, and starts recording with a single button. Afterwards, AI transcribes everything, creates a summary, and extracts key ideas and action items, and makes everything searchable. And then I often use these insights for my future LinkedIn posts or YouTube videos, and it's been incredibly helpful for my startup. I use it at meetings with engineers and mentors, and then I get a clear summary with decisions and action items all in one place. At conferences and meetings, I prefer to use Note Pro. But when I'm driving or walking, I prefer Note Pin S because it makes it completely hands-free. I can wear it as a magnetic pin or clip it into my clothing. My memory is not the best, so I love voice notes because I can stay fully focused on the conversation without worrying about forgetting to write anything down. If you are a founder, researcher, or a consultant, basically anyone who is spending a lot of time on meetings and conferences, this device is definitely worth checking out. You can find it through the link below, and make sure to use my code Anastasia to get 17% off Plot biggest sale of the year. Now, stacking logic on top of logic sounds obvious and elegant, but the moment you split a processor across multiple layers, a new problem appears. Those layers have to communicate constantly, potentially billions of times every second. And this is a part most people miss, because this idea only works if information can almost instantly move between those layers. Otherwise, you've simply moved the bottleneck somewhere else, which means Huawei needs a way to create an enormous number of ultra-fast connections between these folded logic layers. And that brings us to what is arguably the most important announcement of this whole presentation. Huawei is betting its entire scaling roadmap on a single number, 1.5 microns, more specifically 1.5 micron hybrid bonding. Now, that number may not sound particularly impressive, because we used to talk about 2 nanometer, 1.6 nanometer, 14 angstrom transistors. But those numbers describe transistors. This number describes the connections between chips. But when I hear 1.5 microns, my alarm bells start to immediately ringing, because it's incredibly aggressive target. And here's why. Imagine taking two silicon dies and placing one on top of the other, then connecting them with millions, potentially billions of microscopic copper-to-copper links. The more connections you fit, the more data can be moved between layers. And eventually, those separate layers begin to behave like one chip. That's the promise of hybrid bonding. And that's why Huawei keeps talking about 1.5 microns. To put that into perspective, today's state-of-the-art is around 9 micron. AMD's 3DV cache uses bonding pitches around 9 microns. Intel and TSMC are in a similar range. While Huawei is talking about 1.5 micron to 2 microns, and this is incredibly aggressive. And this is not just the bonding challenge. Every time you push to smaller pitches, you need new manufacturing tools, new processes, and new recipes of assembling and testing these devices. That's why this is one of the most interesting parts of Huawei's roadmap to watch over the upcoming years. But solving this communication only gets you halfway there, because then physics shows up. And this one may be even harder. It's heat. Because connecting two logic dies together is one thing. Keeping them cool is another. We already stack memory on top of logic, but memory is relatively passive. Logic is not. Logic switches billions of times every second and generates a lot of heat. That's where things get difficult. Which brings us to the biggest question in Huawei's entire presentation. Because once you stack logic on top of logic, you concentrate a lot more performance into the smaller volume. So your performance goes up, but so does the temperature. This is especially important because Huawei's first target isn't a data center chip. It's Kirin, a smartphone processor. A data center can throw a cooling infrastructure at the problem. A phone cannot. And once you start stacking active logic layers on top of each other, heat becomes crazy difficult to manage. And a data center can use giant heat sinks and liquid cooling infrastructure, but a smartphone has none of that. It's very thin and it sits in your hand. This makes heat Huawei's biggest challenge, because a chip that cannot remove heat cannot sustain performance. And the more logic you stack, the worse it gets. That's why, out of everything in this presentation, thermal story is the most important one to watch, because if Huawei is able to solve it, its roadmap starts to look particularly interesting. If it can't, the entire idea starts falling apart. What they're planning to do with that remains one of the biggest questions. And I recently covered one of the most promising solutions to the heat problem in this episode. Check it out later. But here is a funny part, because apart of this 1.5 micron bonding pitch, which is truly a breakthrough, the rest is nothing new. In fact, the semiconductor industry has been obsessed with timing, because in chips, if signal doesn't arrive in time, nothing else matters. And timing closure in chip design is practically an art form. I know because I used to work in timing sign-off. And I really loved it. It's so stressful at the tape-out time, it's like brain surgery, because you can upsize the cell or move the cell a little bit, and suddenly your whole timing is broken with 1 million possible cell placements. That's why EDA, electronic design automation tools, spend countless hours crunching numbers in the background. They are looking for the most optimal placements of logic cells, making signal path shorter, layout denser, and basically making circuits to meet the timing. In other words, the whole industry has been fighting the distance, so the geometry and timing, for decades. That's why when I was listening to Huawei's presentation, I kept asking myself, haven't we been moving in this direction already? AMD stacks memory on top of the processor. HBM stacks 12 memory dies. And the roadmap doesn't stop there. Engineers are now stacking transistors themselves. Here, you are looking at CFETs, vertically stacked transistors that been developed inside iMac. These kind of devices will likely end up in your phone within the next decade. So this move from 2 dimensions into 3 isn't some radical new idea. What Huawei is proposing is to push that idea to the next milestone. And this brings us to the claim that generated headlines around the world. According to Huawei, with logic folding, they could eventually achieve 1.4 nanometer class transistor density by 2031.
In 2026, logic folding take it all the way to 238 million transistors per square millimeter in one single step.
At the first glance, it sounds impossible, especially without ASML EUV machines. So let's take a closer look. In its dual-layer keyring implementation, Huawei reported a transistor density of 238 million transistors per square millimeter. That's about 55% higher density than its planar design. And that's impressive. But this is where things get controversial, because genuinely speaking, stacking two mature nodes does not create a new manufacturing node. And it certainly doesn't turn a mature process into a true 1.4 nanometer technology. What it does is to increase the amount of logic you can fit into a given footprint. Which is why I would interpret the phrase 1.4 nanometer equivalent very carefully. Which brings us to the bigger question. If tau scaling isn't replacement for transistor scaling, then what is it? Moore's law gave us more transistors for less money. Tau scaling tries to deliver more performance through packaging, connectivity, and system-level optimization. And that's a perfectly valid strategy. But unlike Moore's law, it makes computing more expensive in exchange for performance. So for me, the most exciting part of this story is execution, because everything Huawei is trying to achieve is incredibly difficult, especially at mass production scale. But at the same time, they have fantastic engineering talent. As for whether Huawei and SMIC can close the gap with the world's leading semiconductor companies, that remains the trillion-dollar question. Let me know what you think, and now watch this episode on Chinese EUV replacement, which is being built right now. Love you guys, and I will see you there. Ciao.